The Hong Kong-Zhuhai Macau Bridge is a mega project stretching over 55 kilometers, built right in the middle of one of the busiest seas on the planet. It was once considered an unrealistic idea, as nearly every factor was against it, from powerful currents and weak seabed conditions to the immense pressure of the ocean that could crush any structure. While much of the world remained skeptical, China moved forward and turned that blueprint into reality. This mega project cost more than $19 billion, has a design lifespan of up to 120 years, and is comparable in scale to linking dozens of ordinary sea-crossing bridges together. So how did Chinese engineers manage to lay the foundation and assemble such a massive transportation system in the middle of the ocean? Let Mandarin Tech take you through the answer right now. The Hong Kong-Zhuhai-Macau megaproject is a complex sea-crossing transportation system that connects the three regions of Hong Kong, Zhuhai, and Macau through multiple integrated types of structures within a single route. On the surface of the sea, the most prominent features are three large-scale cable-stayed bridges, Qingzhou Channel Bridge, Zhuhai Channel Bridge, and Zhuzhou Channel Bridge, which are designed to span major shipping channels with significant navigation clearance. Between these cable-stayed bridges lies a continuous system of beam bridges stretching for dozens of kilometers, forming a stable and seamless roadway across the water. However, in areas with dense maritime traffic or strict height restrictions, the bridge cannot continue as a high-elevation structure. Instead, the entire system transitions into an immersed tunnel beneath the seabed. Massive concrete tunnel segments are prefabricated, then transported and precisely installed underwater with extremely tight tolerances. At both ends of the tunnel, the route reconnects to the bridge system via artificial islands constructed in the middle of the sea. Within this entire infrastructure network, the cable-stayed bridges are considered the most technically complex components and play a critical role in ensuring the overall functionality and stability of the entire route. Before the bridge structure rises above the sea surface, the entire project actually begins beneath the water. With weak geological conditions and highly complex construction environments, selecting the appropriate method for building the bridge foundations becomes a critical factor in determining the stability of the entire structure. Currently, three main solutions are commonly used: Cofferdams, Caissons, and pile foundations. Among modern solutions, pile foundations are considered the safest and most flexible option, especially for large load-bearing structures such as sea-crossing bridges. Instead of creating a massive foundation at the surface, this method transfers loads deep into the ground through a system of reinforced concrete piles. The construction process begins with the precise positioning of each pile location, followed by the installation of a steel casing to stabilize the drilling area. The drill bit then penetrates through weak soil layers until it reaches stronger soil or bedrock capable of bearing the load. Once the design depth is reached, a steel reinforcement cage is lowered into place, and concrete is poured from the bottom up using a tremie pipe, minimizing mixing with seawater. The entire process must be carried out continuously to ensure consistent quality. After completion, each pile undergoes strict inspection before proceeding to the construction of the pile cap above. If pile foundations are a way of going deep to find a stable base, then a cofferdam takes a completely different approach. It creates a dry working area right in the middle of the water, so construction can be carried out directly. The principle behind this method is quite straightforward. Instead of working directly in a submerged environment, engineers create a temporary dry space in the middle of a river or sea, allowing construction activities to proceed in conditions similar to those on land. To make this possible, a temporary retaining wall system is installed around the pier foundation location. Typically, steel sheet piles are driven deep into the seabed or riverbed to form a closed enclosure that prevents water from entering from the outside. Once the enclosure is completed, the water inside is pumped out, turning the area into a dry pit surrounded by water. This allows workers to directly access the foundation base, install reinforcement, and pour concrete under much more controlled conditions. However, the biggest challenge of Cofferdam construction lies in water pressure and seepage. When the water level outside is significantly higher than inside the enclosure, hydrostatic pressure can force water through gaps, or even push it upward through the soil beneath the structure. To reduce these risks, the depth of the retaining walls must be carefully calculated, and the dewatering system must operate continuously. Pumps are usually arranged with backup redundancy to ensure the construction area remains dry at all times. After the foundation work is completed, water is gradually allowed back into the enclosure to equalize pressure before the entire temporary structure is dismantled. In areas with great water depth or complex current conditions, engineers often use a particularly stable foundation solution, caissons. Unlike methods that create a dry working space for construction, caissons allow a massive concrete structure to be placed directly onto the riverbed or seabed, where it becomes a permanent part of the foundation from the very beginning. Typically, caissons are prefabricated onshore in the form of large cylindrical or box-shaped hollow structures, then transported to the installation site by barge. When lowered into the water, the entire process is carefully controlled using cranes and positioning systems to ensure the structure is placed exactly at its designed location. The base of the caisson is usually formed with a cutting edge that helps the structure penetrate soft soil layers and gradually settle into the ground below. Once it reaches the required elevation, the interior is filled with materials such as sand, rock, or concrete to increase its weight and secure it firmly in place. Thanks to their large size and heavy weight, caissons provide a very stable foundation for bridge piers that carry massive loads, especially in large river crossing or sea crossing bridge projects. This method allows efficient construction even in deep water environments, while also helping engineers maintain precise control over the position and shape of the foundation from the earliest stages of construction. In many modern mega-bridge projects around the world, caissons have become one of the most important foundation solutions, acting like giant anchors that keep bridge piers stable in constantly changing water environments. After the pier system has been completed and stabilized, the project moves into the stage of forming the bridge deck, the part that directly carries traffic loads and transfers forces down to the supporting piers below. The construction process usually begins by installing temporary support systems or working platforms around the pier area, creating a stable base for the first deck segments. Some initial sections are cast in place to establish the correct elevation and alignment. Next, steel formwork systems are assembled tightly to shape the bridge girders. Inside the girder body, technical compartments are already arranged in advance to support later construction and maintenance stages. As each girder segment is cast or installed into its proper position, it is connected to the previously completed structure, forming a continuous chain that gradually extends outward in both directions. By carrying out construction step by step in this way, engineers can ensure that each installed section achieves a high level of accuracy, while also maintaining structural balance throughout the entire construction process. Constructing the towers and cable-stayed bridge is already a complex task, but on the Hong Kong-Zhuhai Macau Bridge, the process was further restricted by the flight corridor of Hong Kong International Airport. The bridge towers needed to be tall enough to provide sufficient clearance for large ships to pass underneath, yet they were not allowed to exceed aviation safety height limits. To solve this challenge, engineers adopted a completely different approach. Instead of building the towers vertically from the start, each structural segment was first assembled horizontally close to the water surface. A cable lifting system was then used to gradually raise the structure into its final design position. This operation proceeded slowly and under strict control because even a small deviation in force or lifting angle could have caused the entire structure to become unstable. Once the towers reached their upright position, the stay cables began to be installed in symmetrical pairs from both sides. Each cable was tensioned with precisely calculated force to ensure that loads were evenly distributed across the towers and the bridge deck. Even after completion, the bridge still faces serious marine hazards. Strong year-round winds can cause cable vibrations if not properly controlled. Earthquakes and ship collisions are also constant risks, so engineers use damping systems and active marine traffic control to reduce danger. However, the biggest threat comes from chloride ions in seawater. These ions can penetrate concrete and slowly corrode the steel reinforcement inside, weakening the structure over time without visible signs. To prevent this, engineers selected high-durability, corrosion-resistant concrete to ensure a long service life. In the area where this mega sea-crossing bridge passes through, a complex challenge emerged. The same conflict mentioned earlier during the construction of the bridge towers appeared again. The deep-water shipping channel had to coexist with the strict aviation clearance limits of Hong Kong International Airport. This contradiction forced engineers to abandon the option of a continuous bridge and switch instead to a hybrid solution that included an underwater tunnel section. However, one challenge quickly led to another. A transition point was required between the bridge and the tunnel, yet this location had no natural ground suitable for construction. As a result, the only viable solution was to create artificial islands in the middle of the sea. The seabed in this area consisted of dozens of meters of soft marine mud, which was almost incapable of supporting heavy loads using conventional foundation methods. To overcome this, engineers implemented a completely different approach by using massive steel cylinders to form the structural framework of the islands. Hundreds of large-diameter cylinders were transported from distant locations and installed on the seabed with extremely high precision using advanced positioning systems. After being fixed in place, the interior of these circular steel enclosures was filled with material to form a stable foundation platform for the artificial islands. This method significantly reduced the amount of dredging required and helped minimize impacts on the surrounding marine ecosystem. After the artificial islands were completed, they served not only as foundation platforms, but also as transition points for constructing the most complex part of the entire project, the underwater tunnel section. However, a major question remained. How could engineers build a tunnel several kilometers long beneath the seabed while minimizing disturbance to natural water flow in the surrounding marine ecosystem? At first, the option of excavating the tunnel using a tunnel boring machine was considered. However, the geological conditions at the river estuary, combined with strict requirements to avoid excessive disruption to water circulation, made this solution unsuitable. The only practical alternative was the immersed tube tunnel method. With this approach, a large trench is dredged along the seabed, after which tunnel segments are prefabricated on land, towed to the site, and carefully lowered into position for direct underwater connection. Each tunnel segment was enormous, about 180 meters long, several dozen meters wide, and as tall as a multi-story building. Weighing tens of thousands of tons, handling each segment was comparable to maneuvering a massive ship underwater. To ensure construction accuracy, engineers did not cast each segment as a single solid unit. Instead, they divided them into smaller modules for fabrication, which were later assembled under tightly controlled conditions. At the same time, a specialized casting formwork system was developed specifically for the project. Because importing extremely expensive foreign equipment was not feasible, the entire formwork system was designed and manufactured domestically using thousands of tons of steel. To meet the construction schedule, a dedicated production facility was built in a very short time, where thousands of workers operated continuously to manufacture the tunnel segments. Before actual installation began, engineers carried out numerous simulation tests to precisely calculate the forces acting on the cable systems and lifting equipment. In offshore conditions, each tunnel segment had to be lowered into position in muddy water and strong currents, where visibility was almost zero. Even a deviation of just a few centimeters could prevent proper alignment between segments. The combination of massive structural scale, harsh offshore construction conditions, and extremely tight precision requirements made this tunnel section one of the greatest technical challenges of the entire project. After many years of construction under harsh conditions, the Hong Kong-Zhuhai Macau Bridge has not only shortened the distance between three cities, but also changed how people approached the natural limits of the sea. This was not a structure built using just a single construction method. Instead, it is the result of multiple engineering solutions combined into one unified system operating across the open ocean. What makes this project truly remarkable is not simply its size, but the way each challenge was solved with a completely different approach. When engineers could not build higher, they went deeper. When there was no land, they created land. And when traditional methods were no longer effective, they were forced to invent new ones. If you'd like to continue exploring ambitious mega projects like this, be sure to subscribe to Mandarin Tech, where we take you inside the world's most extraordinary engineering works that most people only ever see from the outside.